Well, we've seen what phasors are. Let's see how they might operate. Consider this. We have some vector A, which we have drawn in the x direction here. And let's consider a operator, J, whose action is simply to cause a rotation of this vector A by 90 degrees. So this vector B equal to J times A, or J acting on A, will simply give us the same magnitude vector but a 90-degree difference in phase, rotation. Well, if I were to operate on this again, so I would use the J operator twice on vector A, I would actually go 90 degrees and then another 90 degrees and end up with vector C. Same magnitude, but I end up 180 degrees in the opposite direction, or in other words, C is equal to negative A. If I use the operator one more time, I would go another 90-degree phase, and I would end up with vector D, which would be equal to a negative J times A. And if I would do one more 90 degrees, I would go a full 360 with 4 J operators, and I would end right back up with my vector A. So operating 4 times with this J operator is equal to 1, is equal to A. And we can say that operating twice with this J operator, J squared, would be equal to a negative 1. Let's apply this to the RLC circuit that we have. We can describe the resistance as simply a vector, but then the inductive impedance would be the reactance of the inductance with this J operator, giving it a 90-degree phase in relation to the resistance and the current. And the capacitive impedance would be 3 operators, J cubed, times the capacitive reactance, and that would be a negative J capacitive reactance, because 2 of the J operators would be a negative 1. So our total impedance for a RLC circuit would be equal to R plus J inductive reactance minus J capacitive reactance, or R plus J inductive minus capacitive reactance. We can describe our impedance in this way. The magnitude and phase angle of this total impedance can now be described as before. If we take the square of R in one direction and the square of the J direction, then add those together, we get the magnitude of the impedance. And our phase angle is the inverse tangent of our net reactance over our resistance. So with this new way of looking at it, we can describe total impedance in terms of resistance, which is in ohms, inductive reactance, which is in ohms, and capacitive reactance, which is in ohms. And all we have to do in order to deal with the phase of these 3 things is to use this J operator. Note that twice the J operator is equal to negative 1. Some people would say, well, then the square root of negative 1 would be equal to J. All right. We can resolve any AC circuit into a resistive component and a reactive component. And this would be our basic objective. Here we're looking at a series RLC circuit where our impedance is resistance plus J times our net reactance. And if we can get it into this final form, then we can use our techniques of Chapter 28 with these reactances and the J operator and the resistance to simplify the circuit. Let's try this out with a parallel RLC circuit. Given a parallel RLC circuit with R equal to 10 ohms, L equal to 30 millihenries, C equal to 330 microfarads, and our angular frequency equal to 377 radians per second, what is the impedance of this circuit? All right, so we have these 3 parallel branches. They each have their own separate impedance. If we use our omega, which is 377, the inductive reactance would be 377 times 30 millihenries, 0.03 henries, 11.31 ohms, and the capacitive reactance would be 1 over omega c, 1 over 377 times 330 microfarads, 8.04 ohms. So, if we do the parallel combination of these two reactances, we would have J x sub L times negative J x sub C over J x sub L plus negative J x sub C, using the techniques of chapter 28, product over the sum for a parallel combination. Well, a J times a J is a negative 1, times a negative 1 will give us just 1, and in the bottom we're going to have, if we factor out our J times x sub L minus x sub C. Well, we want to get rid of the J in the denominator. So we're going to multiply top and bottom by a negative J, which will give us 1 in the denominator and a negative J in the numerator. So this is a negative J, x sub L, x sub C over x sub L minus x sub C. We got values for these reactances, and so we can actually get an impedance for this parallel combination. It's going to be negative J, 11.31 times 8.04 over 11.31 minus 8.04. That's a negative J times 27.8 ohms. So now that will represent the parallel combination. So it looks like this. I have a resistance 10 in parallel now with a negative J, 27.8 ohms. Now if I do product over the sum for this, the impedance of that parallel combination, which will be the impedance of the whole circuit, is going to be product over the sum, 10 times a negative J, 27.8, over 10 minus J, 27.8. To try to get rid of the 10 minus J factor in the denominator, we're going to multiply it by its complex conjugate. So we'll multiply it by 10 plus J, 27.8. That will give us 10 squared plus 27.8 squared in the denominator, and we're going to have a J term in the numerator. So this comes out to negative J, 2,780 plus 7,728 over 872.8, which will give us 8.85 minus J, 3.19 ohms. So we have our total resistance and our total reactance for our final circuit, and that will be our impedance for this circuit. The magnitude would be the square of the resistive component plus the square of the reactive component, square root, 9.40 ohms, and the phase angle would be inverse tangent of our reactive component, negative 3.19, over our resistive component, 8.85, negative 19.8 degrees. So this particular circuit, when all is said and done, is more capacitive than it is inductive, because the phase angle is negative. So the voltage lags the current, or the current leads the voltage in this circuit. But the main thing is, if we use this J operator and our reactances, we can use the techniques of chapter 28 that we use for DC circuits and use that on AC circuits, in this case an RLC, parallel circuit. How cool is that? Resonance. In a series RLC circuit, note that when the current reaches its maximum value, it will reach it when the inductive reactance is equal to the capacitive reactance. Because here's our root mean square current for a basic RLC circuit, and that's the root mean square voltage over the impedance. But this value in the denominator will be its smallest value if the inductive reactance equals the capacitive reactance, and hence that'll give us the largest possible current. That'll correspond to when our total impedance is actually just equal to R. So when the impedance equals the resistance in the circuit, we have our maximum current because the reactances are canceling out. This is when resonance occurs. What's actually happening in the circuit is whatever magnetic field you have in your inductor is being transferred as energy to your electric field in your capacitor and back. And that sets up a frequency, a resonant frequency for that circuit. Well, this will correspond to when the inductive reactance equals the capacitive reactance at a particular frequency, which we're calling omega naught. And solving for omega naught, we have that it is equal to 1 over the square root of L times C. And that is our resonant frequency. It will correspond to when the current is at its maximum value. Well, we might wish to set up such a resonant circuit. If we could set up a circuit that is at that maximum value of current, then any kind of disturbance to our circuit will throw that current dramatically off of its maximum value. And hence, we would know when that disturbance had occurred. For instance, consider this RLC circuit. We have a resistance, a capacitance, and we have an inductor, which is really looks like an airport security coil. That's really one big inductor coil like this. And if somebody comes along and they have metal in their pockets or metal on their person, that is going to change the inductance of that coil. And if it changes the inductance of a well-tuned circuit, then it's going to fall off of its maximum value. And if you have a beeper ready to go when the current falls off, you would know when the inductance had changed when somebody has metal on their person. So it's a great device to use for security at the airport. Here's another one. Say I have an inductor underneath the ground. It's underneath the road, and along comes a car. And doesn't have to go through the inductor, it just has to go in the vicinity of this coil to change the magnetic field and change the properties of the inductance. So it will change the inductance of that coil, take it off of its resonant frequency at that moment, and its maximum current. When the current drops down quickly, then you have a beeper go off, and you know, at least in this case, that the traffic light needs to change. Tuning to a radio station. Different resonant frequencies are obtained either by changing the capacitance or the inductance, and hence changing the resonant frequency, allowing you to pick up the airwaves and magnify that particular airwave that you wish to receive. We could do that by having some kind of core within the inductor, which we can move back and forth, maybe with a knob, and that will help us change the station. Or you could have the same kind of thing happen with your capacitor, because we know the capacitance changes with its width. So if we were to move its width, we would change the frequency of this circuit and hence change the station as well. That's kind of a simplified idea of what's going on, but basically that's how a radio or a TV would work. Let's try this out. An RLC circuit is used in a radio to tune to an FM station broadcasting at 99.7 megahertz. The resistance in the circuit is 12 ohms and the inductance is 1.4 microhenries. What capacitance should be used? Well, our angular frequency is going to be 2 pi times the frequency of the station, 99.7 megahertz. That's going to be 6.26 times 10 to the 8 per second. And hence, we want an angular frequency equal to 1 over the square root of L times C. So if we reverse engineer this formula, we can calculate the capacitance we need. Square both sides, solve for C, and C will equal 1 over the inductance times the angular frequency squared. That's 1 over 1.4 microhenries times 6.26 times 10 to the 8 radians per second squared. We need a capacitance of 1.82 times 10 to the minus 12 farads, 1.82 picofarads. If we had that in our circuit, it would have the right resonance to pick up that station. The third special topic for this lecture is filter circuits. Consider this circuit where we have an AC source, we have a capacitor and a resistor in series, and our output is going to be across the resistor. If we consider only maximum values, we would have that our in voltage would be equal to the current times the impedance. And the impedance in this case is going to be equal to R squared plus the capacitive reactance squared, square root, R squared plus 1 over omega C squared, square root. And hence by voltage division, our maximum output voltage will be equal to the ratio of the resistance to the impedance times our voltage in. So our ratio of our output to our input would look like this: R over the square root of R squared plus 1 over omega C squared. But note what happens when the frequency of our signal changes. If our angular frequency approaches 0, we're going to have something that is infinitely large for 1 over omega C, and then that is going to be 1 over the square root of something infinity, which will mean basically 0. So our V out over V in will be 0, and our V out will approach 0. Anything with low frequencies is not going to make it to our output. What would happen if omega were high frequency? If omega were high frequency, we would have 1 over high frequency, which is basically 0, and we would have R over the square root of R squared, which would be R over R. It would approach 1. So our output would approach everything of our input. So for high frequencies, just about everything makes it out. This sort of configuration where we have a capacitor and resistor in series, and we have our output, in this case on the resistor, is called a high-pass filter, because only high frequencies are passed. If I have a signal that has a bunch of frequencies, the low frequencies would be blocked out, and the high frequencies would pass through. So it filters out the low frequencies. Let's reverse the components. Let's put our output on the capacitor. Now our output is equal to the current times the capacitive reactance. And our ratio of our output to our input is 1 over omega C over the square root of R squared plus 1 over omega C squared. What happens when this circuit, when the frequency approaches low values? Well, if it's low values, we're going to have basically infinity in the denominator and infinity in the numerator. And actually, infinity over infinity is actually 1. So for low frequencies, those are going to make it through. For high frequencies, this thing is going to approach 0. So this is actually a low-pass filter. It'll filter out the high frequencies and pass the low frequencies. Consider the circuit shown where we have a capacitor and a resistor. Calculate the gain V out over V in for omega equal to 300 radians per second. Where our capacitive reactance will be 1 over omega C, 1 over 300 times 0.09 microfarads, 3.7 times 10 to the 4 ohms. And hence, our ratio of our V out over our V in will be resistance over the impedance, 800 over 800 squared plus this 3.7 times 10 to the 4 squared, square root. That will give us a V out over V in of 2.16 times 10 to the minus 2, or only about 2%. So that frequency of 300 per second, only 2% of that signal is going to make it through. But what happens if the frequency were 7 times 10 to the 5 per second, much, much higher? Well, now our reactance, our capacitive reactance, is 1 over omega c. 1 over 7 times 10 to the 5 radians per second over 0.05, 10 to the minus 6 farads. Is 6.3 times 10 to the minus 2 ohms. And our V out over our V in will be 800 over 800 squared plus this 6.3 times 10 to the minus 2, which is basically 0. And we take the square root of 800 squared, that would be 800 over 800, basically. This is 0.9998. 99.98% of that signal makes it through. So the high frequency is passed. The low frequency, only 2% of that makes it through. This is a high pass filter. That concludes the second lecture in Chapter 33 on AC circuits.